Hi, I'm Graham North, and I've got currently a project going here which I'm going to get Claude to explain to you. I'm doing this in person, so you know there's a real person there and it's not just something that's been randomly generated. This machine here, you can see, is an Apple Mac. It's an Air with an M1 chip. And you can see I've got a monitor running on it, of course. This is actually running now. There's a fan behind it as well because it doesn't have a fan internally. And here, this is just a slide that I got generated. Well, it's a document I got generated which has the stats of it. The point of this is to try and actually have Asahi Linux, which is the default installation for Linux on the Mac, which is currently running, to have its Vulkan system run models, AI models, and specifically in this case it's llama.cpp, to have that run models on the M1 chip in Linux at the same speed as it does currently in Mac. And as you can see here, we've got some stats already. We've made a lot of progress. The original stat for Mac metered by running it on it is 272 tokens per second, and the original stock Vulkan, which is what I started with about a month ago now I think, was just over 90 tokens a second. So it worked, it was just slow, and a third of the one that runs in Apple. This is a dual boot system, so there's Apple Mac installed, and I've repartitioned it to add in the Asahi Linux installation. Currently we're at just short of 220. There's been a lot of refinement. Some of the hardware instructions have been uncovered. Claude itself has access. This desktop, which is actually out of shop, but it's basically a desktop that's running here, communicates with this over the network, and it has the ability to automatically reboot it into Mac and Asahi. And I've had it doing it for the last month. It struggles sometimes because there's a lot of dead ends and it's polluted the context a bit, so I'm revising it now. But it's so far achieved 220 tokens a second, so 80% of what's running on Mac. And it really actually does respond. This is not just a technical benchmark. You can query it and it will return with that sort of thing, which is actually a reasonable speed. But the objective is to actually beat the Mac one. So I want it above, I want it in the, the 280 to 300 tokens a second. I don't know if that's achievable, but certainly equaling is achievable because it's the same hardware. The only difference is the software. And so I'm getting Claude. It's currently on Opus 4.8 to render it. You can see it's actually working there. This is producing the slide presentation that you're about to see. And I'm just doing this in person so you can see what's going on. You can see there's an actual real person behind this. It's not some random guy that's generated something stupid or somebody that's done something that isn't actually working on this and just trying to do some marketing. So I hope the presentation is clear. I've tried to make it so that it actually starts with just basic engineering knowledge and it actually works right through to the low-level stuff running on a GPU. Myself, I have experience with working with the hardware. I've written shaders, OpenGL stuff as well, and I've also written CUDA stuff. And so I actually understand the technical detail behind this. I understand how the GPU executes the matrix multiplications that are part of a pipeline when it's doing when it's processing a prompt, basically. And I know what's going on and I know how it works. And so it's not that I'm doing something, I'm getting Claude to do something that I don't know how to do myself. It's just that it does it a lot quicker, and obviously it can sit there working 24 hours without breaks, and that's what it's been doing. And it works, to my opinion, it works roughly 5 times the speed I can run. So I make no aspirations as to the quality of my engineering, but I'm metering it at roughly 5 times the speed that I can work at when it's working constantly and when I'm working constantly. But of course it can work for 24 hours while I'm sleeping and then taking breaks. And so the timelines are obviously a lot shorter. So anyway, I hope the presentation is reasonable, that it makes sense to you, I've generated it on an actual local LLM using Claude to generate the presentation itself, but the audio and the TTS processing is done by a machine that I've got with a 3060 and Kokoro and an FFmpeg accelerated installation as well. So don't forget to like and subscribe. Apparently commenting on the video brings it higher in the algorithm so that people can see it. And I will be posting in the description all of the details of the repos that are used, which are going to be shared online. There's posts in the community as well. So like and subscribe, click the notification bell or whatever, and I hope it's okay. Thanks.
Welcome. Over the next hour, I'm going to walk you through a single, focused engineering project. Making a large language model run on an Apple laptop's graphics processor at the same speed you'd get from Apple's own software, but doing it entirely with open-source Linux and a community-built graphics driver. This talk assumes you're an engineer. You understand hardware and software in general terms, but I will not assume you know anything about this particular chip, this particular driver, or how a graphics processor multiplies matrices. We'll build all of that up together. We'll start high with the problem and why it's hard. Then we'll get concrete about the machine and the software stack. And then we'll go all the way down to the individual instructions the graphics processor executes, and to the registers and the tiny matrix engine inside it. Not quite down to the transistors, but close. Let's begin. Here is the shape of the problem. We have one physical laptop, an Apple M1 with a 7-core graphics processor, and it can boot two completely different worlds. On one side is Apple's world, the macOS operating system, Apple's Metal graphics interface, and Apple's own closed compiler and driver. This has been tuned for years by the people who designed the chip. It is our reference, the speed we're trying to reach. On the other side is the open world, Asahi Linux, which brings Linux to Apple Silicon, the Vulkan graphics interface, which is the open industry standard, and Mesa, a graphics driver that the community reverse-engineered from scratch because Apple never documented this hardware. In this world, every layer is open source. We can read it and we can change it. The workload is a language model, specifically reading a prompt, the phase called Prefill, which is essentially one giant sequence of matrix multiplications. The central question of this whole project is simple to state. On the identical chip, can the open stack go as fast as Apple's? And when it doesn't, we want to know exactly which layer is leaving speed on the table. Every engineering project needs a number, and ours is this: 272 tokens per second. That's how fast Apple's stack reads the prompt on this specific laptop. It's not a marketing figure from a spec sheet. We measured it ourselves on the machine. Where are we today? The open stack runs at 210 tokens per second on its baseline, and 220 with one extra optimization enabled. So we're at roughly 80% of Apple's speed, and the remaining gap is what this project is about. Now, the most important rule of the whole effort, and the one that's easiest to cheat on, is correctness. A language model does an enormous number of arithmetic operations, and it's very easy to make a change that runs faster simply because it's quietly skipping work or producing garbage. So we hold every single result to a hard standard. The output must be numerically correct, checked against a known good reference and against the model's perplexity, a measure of its prediction quality. If a change is faster but the numbers are wrong, it doesn't count. It's not a win, it's a bug we caught. You'll see this rule save us several times later on. Let's meet the machine. It's a completely stock Apple M1 MacBook Air, the entry-level one. The graphics processor inside is codenamed G13G. It has 7 graphics cores and 8 GB of memory, and crucially that memory is shared between the main processor and the graphics. There's no separate graphics card. This matters later, because it means feeding data to the matrix engine is often the bottleneck, not the arithmetic itself. The laptop dual boots. Hold a key at power on and you get macOS. Otherwise it boots into Asahi Linux, the project that brought Linux to Apple Silicon. Only one operating system runs at a time, but it's physically the identical chip either way. That's what makes this a fair fight. We measure Apple's speed under macOS, reboot into Linux, and try to match it on the same silicon with the same model and the same benchmark. There's one very practical wrinkle. The machine gets a new network address almost every time it reboots, and it hops between two different subnets. So a surprising amount of the lab plumbing is simply finding the machine again and reconnecting. We track it down by the fixed hardware address of its network card. Before we go deeper, it's worth appreciating the two chores that bracket every single working session, because getting them reliable was real engineering in its own right. The first chore is simply finding the machine. As I mentioned, the laptop's network address changes on almost every reboot, and it hops between two different subnets depending on how it comes up. Chasing that by hand is maddening, so instead we locate it by the one thing that never changes, the fixed hardware address burned into its wired network card. We scan the network for that address, and then, crucially, we connect and ask the machine which operating system it's actually running, rather than trusting any cached guess. That check alone eliminated a whole category of confusing mistakes, where you think you're measuring Linux and you're actually on macOS, or the reverse. The second chore is flipping which world it boots into. To measure Apple's reference speed, we need macOS, so we tell the boot manager to start macOS the next time only, and reboot. It's deliberately a one-shot. The boot after that automatically returns to Linux. And to go back the other way, there's nothing to undo at all. A plain reboot lands in Linux again. That little asymmetry is a nice piece of design, because it means the system always drifts back to our working environment on its own. Automating both chores turned a fiddly, error-prone ritual into two reliable commands, which matters enormously when a fair comparison depends on measuring the exact same machine both ways. When the model wants to multiply two matrices, that request falls through 6 layers of software before a single number is computed. Understanding these layers is the map for the whole talk, because performance can be won or lost at every one. At the top is llama.cpp, the application. It loads the model and runs the benchmark. Below it, a library called ggml builds a graph of operations. The one that dominates our workload is a big matrix multiply. That request then goes to Vulkan, the open, cross-industry graphics and compute interface. In Apple's world, this layer would be metal instead. That's the main fork in the road between the two stacks. Vulkan hands the work to Mesa, the open-source driver. The Apple Silicon variant is nicknamed Honeykrisp. Mesa's job is to take our shader program and compile it into actual machine code for the graphics processor. The part that does that deep inside Mesa is called the AGX backend. It turns the shader into Apple GPU instructions and decides how to use the chip's registers. And finally, at the bottom, the 7-core M1 graphics processor executes those instructions on its matrix engine. Almost all of our engineering work lives in that AGX backend, the second from bottom layer, because that's where the machine code is actually shaped. Let's line the two stacks up side by side, because the comparison tells us exactly where to look. On Apple's side, the metal graphics interface, Apple's closed compiler and Apple's closed driver. On our side, the Vulkan interface, Mesa's open compiler and Mesa's open driver. But look at what's identical on both paths, and this is the key insight. Both run the very same llama.cpp application. Both run the very same quantized model. Both drive the very same 7-core M1 graphics processor. And here's the crucial part. Both ultimately issue the very same hardware instruction, a matrix multiply and add that Apple's chip executes natively. So the arithmetic at the bottom is identical. The chip is identical. The only real differences are in that middle band, the interface, the shader language, and the compiler, which means logically any speed gap between the two must come from how the compiler shapes the code, how many instructions it emits, how it schedules them, and how it uses the registers. That single deduction is what points all of our work at the compiler, and it's what the transplant experiment at the end of this talk will prove with a hard number. We should be precise about what we're measuring, because a language model actually runs in two very different phases. The first phase is called Prefill. This is where the model reads your entire prompt at once, hundreds of tokens in parallel. Because everything is processed together, it turns into big, dense matrix multiplications. This phase is limited by raw compute and by memory bandwidth, and it is exactly the phase where the matrix engine matters most. This is what we optimize. The second phase is generation, producing the answer one token at a time. Each step is a small, skinny multiplication, and it's limited mostly by how fast you can stream the model's weights from memory. It's a genuinely different engineering problem, and it's not today's. Our benchmark is called PP512, or Prefill 512. Hand the model a 512 token prompt, and report how many tokens per second it can process. Apple's stack scores 272. Ours scores 210 to 220. Everything in this talk is aimed at closing that gap on that one number. Now the model itself. Llama 323B has about 3 billion numbers in it, its weights. If we stored each one at full precision, that's 16 bits each, which is both too large to fit comfortably and too slow to stream from memory on a shared memory laptop. So the model is compressed using a scheme called Q4K-M. The idea is to store each weight in only about 4 bits. You take a group of weights, a block, and instead of storing each one precisely, you store a couple of full precision scale factors for the whole block. And then each individual weight becomes just a small integer that you interpret relative to those scales. Here's the consequence that will matter enormously later. Before the matrix engine can multiply anything, the graphics processor has to reconstruct each real weight. Read the tiny 4-bit integer, read the block's scale factor, and multiply them back to a real number. That step is called dequantization, and that reconstruction is not free. It costs extra instructions, and this is the subtle part: it costs registers, the GPU's scarcest resource, right in the innermost, hottest loop of the code. A big chunk of this project turns out to be a fight over those registers, and the dequantization math is one of the main things consuming them. When you're optimizing hard, the most dangerous results are the ones that look like triumphs but are actually bugs. So we have 2 gates that everything must pass. The first is the oracle, a correctness test. It multiplies matrices whose answer we already know and compares the GPU's output, number for number, against a trusted reference. It has to match perfectly, 947 out of 947 cases. The second is Perplexity. This runs the actual model on actual text and measures how well it predicts. Essentially, is the model still smart? The correct value is about 1.01. A broken kernel produces astronomically wrong perplexity. Why does this matter so much? Because we genuinely hit these traps. One tile configuration scored 371 tokens per second, comfortably faster than Apple. We were briefly thrilled. Then it failed the oracle. It was fast because it was quietly skipping work and producing wrong numbers. Another scored 215, but its perplexity was 3 times 10 to the 14th, complete garbage. So the standing rule is, any result faster than Apple is guilty until proven correct. We check the oracle and perplexity first, and we celebrate second. That discipline is what keeps every number in this talk honest. Let me show you a real sweep of a single tuning knob, the tile shape, because it's the perfect illustration of why the discipline matters. Read the speed column first, and let yourself be tempted, because we were. The narrow tile setting scored 371 tokens per second. That is dramatically faster than Apple's 272. For a moment, it looks like we've won the entire project in one line of code. Then it fails the oracle. It's fast precisely because it's quietly skipping work and producing nonsense. The medium tile scored 215, still faster than our real baseline, still exciting. Its perplexity comes back as 3 times 10 to the 14th. The model has been reduced to gibberish. The thin tile scored 114 and also fails. Its numerical error is far outside tolerance. Starved of the data reuse it needs, it computes the wrong thing. And then the balanced tile, 191 tokens per second, slower than 3 of the 4, but it passes the oracle perfectly, 947 out of 947, and its perplexity is a healthy 1.01. It is the only honest number on the table, and it's the one we keep. This is the whole game in one slide. The fastest looking result was the most broken. Without correctness gates, we'd have proudly reported 371 and shipped a model that outputs garbage. The gates are not bureaucracy. They are the difference between engineering and self-deception. To close a performance gap in a compiler, you have to see what the compiler is doing. But Apple never documented this graphics processor's instruction set at all. So the community reverse engineered it and built an open tool called ApplePoo, a disassembler and assembler. It turns raw machine code bytes into readable instructions and lets us write instructions back into bytes. This tool is central to everything that follows. With it, we can do something powerful. On macOS, we can reach in and extract Apple's own compiled matrix multiply kernel, the exact machine code Apple's compiler produced, and disassemble it. That gives us a gold standard reference. This is what good looks like on this chip. Then we can put the 2 side by side and diff them, instruction by instruction. Apple's compiled code versus Mesa's compiled code for the identical piece of math. And the headline from that comparison frames the entire problem. For the same matrix multiply, Apple's compiler emits roughly 350 instructions. Mesa emits over 1700. Same chip, same result, nearly 5 times the instructions. Closing that ratio, teaching the open compiler to be as terse and as clever as Apple's, is what the rest of this talk is about. Now let's actually read the gap, because this comparison is what turns a vague complaint "it's slower" into a precise engineering target. Here is Apple's compiled kernel next to ours, for the identical matrix multiply. Total instructions, Apple 352, us 1734, nearly 5 times as many. Address arithmetic operations, the instructions that just compute where in memory to read and write, doing no actual math on the model. Apple uses 54. We use 115. Memory stalls, the moments where the processor has to wait for data to arrive. Apple 5, us 52. And registers, as we've seen. Apple around 104, us 159. But here is the single most important line, and it's the one that isn't in the table as a difference. The actual matrix instructions are identical. 32 of them on each side. Apple is not using some secret, faster multiply that we don't have access to. The engine does the same work for both of us, so the entire gap is everything around the multiply. It's the addressing arithmetic, the scheduling of memory operations, and the register usage. Every one of those is a pure code generation decision made by the compiler. This table is, in a sense, the whole thesis of the project on one slide. The hardware is even, the multiply is even, and all the difference is in how cleverly the compiler wraps the multiply. That's a fixable kind of gap, and it's exactly where all our wins came from. It's worth being honest about what this environment is actually like, because it shapes how the work gets done. This is not a clean simulator. We are driving real graphics hardware at the instruction level, and when you do that, you have to live with how it fails. When a kernel is wrong in the wrong way, it doesn't just return a bad answer. It wedges the GPU completely. And on Linux, Asahi can't always reset a hung Apple graphics processor, so the entire laptop hard reboots. We have lost the machine this way many times. To make that survivable, there's a watchdog armed to automatically reboot a frozen GPU after 120 seconds. So a hang costs a couple of minutes, not a destroyed session. The key working habit that falls out of this: iterate on the safe test, not the risky one. The correctness oracle is rock solid and essentially never wedges the machine, whereas the full benchmark occasionally does. So we do all our debugging against the oracle, and only run the benchmark when we specifically need the speed number. And every experiment is built to be reversible. Each change hides behind a switch that defaults to off, so the known good baseline is always exactly one setting away. When you might reboot the machine on any run, that discipline is survival. If you strip away the reboots and the network hunting, the actual daily rhythm of this project is a tight, repetitive loop over the compiler. It's worth seeing it laid out, because every result in this talk came out of this cycle. Step 1, edit the Mesa AGX backend, change something about how it generates code. Step 2, rebuild the driver, which takes a few minutes. Step 3, run the correctness oracle. If it's not perfect 947 out of 947, we reject the change immediately, no matter how promising it looked. Step 4, run the benchmark and the perplexity check. Is it actually faster, and is the model still correct? Step 5, and this is the intellectually interesting part. Disassemble the result and diff it against Apple's kernel to understand why the number moved, how many instructions, how many registers. And step 6, if it's a genuine correct win, we keep it behind a switch, otherwise we revert. We run dozens of these cycles per session, and the honest truth is that most changes are neutral or slightly negative. The wins are rare, and every one of them was hard-won through this loop. The rest of the talk is really the story of the handful of changes that survived it. Now we go under the hood. Everything in Prefill reduces to one operation repeated at scale, multiplying matrices. So if we understand a single matrix multiply, we understand the whole workload. The operation itself is simple to state. You take a row from one matrix and a column from another, multiply them together element by element, and add up the results. That gives you one number in the output. Then you do that for every combination of row and column. For our shapes, that's millions of multiply and add operations, but in a completely regular, predictable pattern. And regular, predictable arithmetic is exactly what specialized hardware is built to accelerate. Here's the subtle crux, though: arithmetic intensity. Each weight gets used only a little before the machine needs to go fetch the next one. So the processor actually spends a lot of its time fetching weights and reconstructing them from their compressed form, rather than doing the multiplications themselves. That's why earlier I said Prefill is partly memory-bound rather than purely compute-bound. Keeping the arithmetic units fed is half the battle. The hardware's answer to all this is a dedicated matrix engine, a unit that performs an entire small matrix multiply in a single instruction. Let's go meet it. Let's look a little closer at that compression scheme, Q4K, because reconstructing these weights is one of the two things that will turn out to be eating our registers. The weights are organized into superblocks. Each superblock is 256 weights, packed into 144 bytes. It carries two full precision master values, a master scale and a master minimum. Then it's divided into 8 subblocks of 32 weights each. Every subblock has its own small 6-bit scale and minimum, derived from the masters, and each individual weight is just a 4-bit integer. So to recover one real weight, the GPU takes the 4-bit integer, multiplies it by the subblock scale and subtracts the subblock's minimum. That's a handful of arithmetic operations, but per weight, every single time that weight is used. Now multiply that by the millions of weights streaming through the inner loop. That reconstruction math becomes a serious consumer of instructions, and more importantly, of temporary registers. Hold on to that thought, because in a few slides we're going to literally count the registers in the hot loop, and the dequantization temporaries are one of the biggest culprits. So what's actually inside this graphics processor? Let's build a picture of the parts that matter. There are 7 GPU cores, running at up to roughly 1.3 GHz. Each core doesn't run just one thing, it juggles many groups of threads at once, switching between them to hide the latency of waiting on memory. This is the fundamental trick of GPUs. When one group of threads is stalled waiting for data, the core runs another. Those threads don't run individually. They run in lockstep bundles of 32, that's the natural width of this hardware. All 32 share a single instruction stream, but each one operates on its own data. When you hear 32 threads moving together, think of one instruction fanned out across 32 lanes. Each core has a large register file, fast local storage for the numbers threads are actively working on, and it's shared out among all the live threads. This register file is the central scarce resource of the whole system, and it is the lever we end up pulling hardest. And finally, the star of the show. Inside each core sits a dedicated matrix engine. It multiplies small, fixed-size tiles of numbers directly in hardware, dramatically faster than grinding them out with ordinary multiply instructions. That engine is what we point our language model at. We keep saying the hard part is feeding the matrix engine, not the multiply itself. Let's make that concrete by looking at the memory hierarchy, because that's where the real fight happens. There are 3 tiers and they trade size against speed. At the bottom is main memory, the 8 GB shared between the main processor and the graphics. It's large enough to hold the whole model, but it's far away in processor terms, and because it's shared, its bandwidth is precious. The model's weights live down here. In the middle is shared on-core memory, a small, fast scratchpad that each thread group uses to stage slabs of weights and activations. The point of it is reuse. Load a slab once into the scratchpad, and all 128 threads in the group can read it many times without going back to distant main memory. And at the top are the registers, the fastest storage of all, right at the arithmetic units. The matrix engine reads its inputs only from registers, nothing else. So the entire job of the kernel is a bucket brigade. Weights flow from main memory, into the shared scratchpad, into registers, and finally into the engine. And the art is keeping every stage of that brigade busy so the engine at the end never sits idle waiting for the next bucket. When you hear that most of our optimizations are about paired loads, or staging, or register pressure, what they really are is grease on one of these handoffs. Keep the brigade flowing, and the expensive matrix engine stays fed. Here is the single most important instruction in this entire talk. It's called simd-matrix-eff-madd, and it performs a matrix multiply in one instruction. What does it actually do? It takes one 8x8 tile of numbers and another 8x8 tile, multiplies them together, and adds the result into an 8x8 accumulator. That's 512 multiply-add operations, expressed as a single instruction, and executed by the dedicated matrix engine across the 32-lane bundle of threads. One instruction, an entire tile of arithmetic. The name is a perfect description if you decode it. Simd means it acts across all 32 lanes at once. Matrix means it's operating on tiles, not scalars. And eff-madd stands for fused multiply-add, multiply and accumulate in one step. And here is the catch that defines the whole optimization problem. The matrix engine can only stay busy if those input tiles are sitting ready in registers, at exactly the moment it needs them. If the tiles aren't ready because you're still fetching weights, or reconstructing them from their compressed form, or you've run out of registers to hold them, the engine stalls and waits. So the hard part is never the multiply itself. The hard part is feeding it. Almost everything that follows is about keeping this one instruction fed. A single prefill matrix multiply is enormous, far too big to do all at once, so it gets chopped into tiles and spread across the GPU's thousands of threads. And how you chop it up is one of the real tuning knobs. The output matrix is divided into tiles. Each group of threads, a thread group, 128 threads working together, takes responsibility for computing one output tile. Within that thread group, the 32-lane bundles cooperate. They load slabs of weights and activations into fast on-core shared memory, and then feed the matrix engine tile by tile, marching step by step along the shared dimension of the multiply. Now, the size of these tiles is a genuine trade-off, and it's a recurring theme. Bigger tiles let you reuse each loaded value more times, which is efficient, but they need more registers to hold all those intermediate results. Smaller tiles need fewer registers, but they reuse data less. On this small 7-core chip, which is tight on register capacity, smaller tiles often win, and that was one of our earliest measured gains, worth a few %. Get the tiling wrong in either direction, and you either starve the matrix engine or blow the register budget. So it's the first dial we reach for, but, as we'll see, far from the last. We keep coming back to registers, so let's make it precise why they govern everything. Registers are the fastest storage on the chip, the small pool of scratch space sitting right next to the arithmetic units. They are the only place the matrix engine reads its inputs from directly. Every value a thread is actively working with lives in a register. The problem is scarcity. Each core has a fixed pool of registers, and that pool is divided among all the threads running on the core. So there's a direct tension. If each thread demands more registers, then fewer threads can run at the same time. Registers per thread and threads per core trade directly against each other. And that trade is the crux, because remember, the GPU hides memory latency by having many thread bundles ready, so that when one stalls waiting on a load, another can run. If each thread hogs too many registers, you can only fit a few bundles per core, and when they all stall, the core just sits idle. Fewer threads means less ability to hide latency. Worse, if a kernel needs more registers than are actually free, it spills. It's forced to park values out in slow memory and fetch them back. In a hot inner loop, that's catastrophic. So the entire kernel design is a tightrope walk around this register limit. On the next slide, that tightrope becomes a concrete table of numbers. This table is the heart of the whole project, so let's take it slowly. On this hardware, the number of registers each thread uses maps, in hard discrete steps, to how many threads a core can run at once. It's a staircase. If a thread uses 104 registers or fewer, the core can run 1,024 threads. Let it creep up to 128 registers, and you drop to 832 threads. At 160 registers, you're down to 640. Now here is the entire problem in two numbers. Apple's kernel uses about 104 registers per thread, so it sits in the top tier, running 1,024 threads per core, with maximum ability to hide memory latency. Our hot kernel uses 159 registers, which pins it to the 640 thread tier. That's roughly a 1.6 times occupancy disadvantage, baked in before we do anything else. So the central lever of the project becomes crystal clear. Get our register count down from 159 toward 104, cross those staircase boundaries, and unlock more concurrent threads. Almost every optimization we chase is ultimately trying to move our number down this table. And the beautiful thing is we can measure exactly where we sit with a single command, no guessing. So how does a portable, vendor-neutral program end up issuing Apple's very specific matrix instruction? Through a feature and a translation step. The feature is called cooperative matrix. It's Vulkan's standard, portable way for a shader to say, multiply these tiles of numbers together without naming any particular chip. The same shader could run on an Apple GPU, an NVIDIA GPU, or an Intel GPU. Mesa's AGX backend is what makes it real on this hardware. It translates that portable request into the actual simd-matrix-eff-madd instructions we met earlier, carefully arranging the data into the 8x8 shapes the engine demands. Turning this path on was a genuine milestone in the project. Before it, we had a scalar approach, grinding out the multiplication one operation at a time, and it ran at about 127 tokens per second. Routing the work through the real hardware matrix engine jumped us to 180, and then to 191. A huge step purely from using the right instruction. But that same milestone is exactly where the register problem was born. The fast matrix path is precisely the code that needs 159 registers per thread. The speed and the register pressure arrived hand in hand, which sets up the fight for the rest of the talk. Let's zoom all the way in and walk through what a single matrix multiply kernel actually does from start to finish, as a stream of instructions on the hardware. This is about as close to the metal as we'll get. It happens in 3 acts. First, the preamble setup code that runs once, before the main threads even launch. Its job is to load the addresses of the data buffers and the matrix dimensions into a special, shared set of storage called uniform registers, values that every thread can see. Remember this preamble. It becomes surprisingly important in the transplant experiment later. Second, the hot loop, and this is where essentially all the time goes, because it runs hundreds of times. Each iteration does 4 things. It issues a device load to fetch a slab of weights and activations from memory. It dequantizes, reconstructs the real weights from their 4-bit compressed form. It then issues a burst of those simd-matrix-eff-madd instructions, feeding tile after tile to the matrix engine. And then it advances 1 step along the shared dimension of the multiply, and does it all again. Third and finally, the store epilogue code that runs once at the end to write the finished output tile back out to memory. This ending turns out to be surprisingly bloated in our version, and it becomes an optimization target of its own. Set up hot loop store. That 3-act structure is the skeleton underneath every number in this talk. We keep saying the hot loop uses 159 registers, but which parts of the code are actually using them? We can answer that precisely with a profilling command that breaks the demand down by category, and the answer reshapes the whole strategy. Here's the breakdown. The accumulators, the registers holding the actual result we're computing, take about 32. The staging of the matrix tiles takes about 24. Address arithmetic, computing where in memory to read and write, takes about 46. And the dequantization temporaries, the scratch values from reconstructing those 4-bit weights, take about 57. Now look at the shape of that. Only about 32 of the 159 registers are the actual result. The other 100 plus are overhead. Address arithmetic and dequantization scratch. And that's the good news, because overhead is reducible. We can't shrink the result, and shrinking the tile hurts reuse. But the addressing and the dequant temporaries are exactly the kind of thing a smarter compiler can compute more cheaply, or throw away and recompute later. So the plan crystallizes. Attack the addressing and dequant registers, drive the count down, cross one of those occupancy steps and unlock more threads. This is the open lead of the project, the next real gain, and it's pointed at a specific measured target rather than a guess. So what actually moved the number? It's worth seeing the ledger, because the honest lesson is that there was no single silver bullet. Progress came from a stack of correct, measured, individually modest improvements that compounded. Routing the work through the real hardware matrix engine, instead of scalar multiplies, took us from 127 to 191, the big one. Shrinking the tiles to cross an occupancy step added almost 7%. Pairing up memory loads, fetching 2 values in 1 instruction to halve the load traffic, added nearly 8%. Smarter instruction scheduling, reordering the code to hide latency, added another 7. And pre-unpacking the block scales, reconstructing them once when the data is loaded, rather than every single time a weight is used, added 4.5%. Notice a few things about this table. Every single row passed the correctness oracle and the perplexity check. None of them are fast but wrong. Every row hides behind a switch, so the baseline is always recoverable. And none of them is glamorous on its own, but compounded together, they carried us from an early 91 tokens per second up to 210, and 220 with the scales optimization on. That's the texture of real performance work. Many small verified wins stacked patiently. Here's a genuinely surprising result. The kind of thing you only find when you actually read the disassembly instead of guessing. We knew our kernel had 52 memory stalls to Apple's 5, and the natural assumption is that those stalls are scattered through the hot loop, slowing down the multiplication. So we looked. And the twist is this: only 4 of our 52 stalls are in the hot loop at all. The other 48 are in the store epilogue, the little bit of code that runs just once at the very end to write the finished answer back to memory. Why on earth would writing out the answer cause 48 stalls? Because of how our compiler does it. To write the finished tile back, our compiler emits 96 separate single-value store instructions, 1 number at a time. Apple, for the same write-out, emits just 8 stores, each one bundling several values together in a single operation. Ours is a slow drip, Apple's is a handful of efficient pause. The insight here is important and a little humbling. A big chunk of our gap has nothing to do with the matrix multiplication we've been obsessing over. It's a clumsy, unbundled write-out at the end of the kernel, and it's a completely separate optimization from the register pressure work, with its own fix. Teach the compiler to bundle those stores the way Apple does. So now we have 2 independent, well-understood targets, the register pressure in the loop and the bloated store at the end. Neither is a mystery anymore. Both are just code generation waiting to be improved. Of all the results, the most satisfying wasn't a tuning tweak at all. It was discovering that the open compiler itself had a genuine bug, that it was quietly doing something dangerously wrong. The symptom was strange. There was an entire category of optimization that had been switched off, because whenever anyone turned it on, the model's output got corrupted. It was treated as cursed, avoid that path. But nobody knew why. So we hunted it down, and this is exactly where the safe correctness oracle earned its keep. Because we could run the oracle over and over without wedging the machine, we could bisect the problem methodically until it collapsed to a single cause. The instruction scheduler, the part of the compiler that reorders operations to run faster, was reordering the memory operations that spill registers. It was letting a spilled value be read back before it had actually been written. A classic ordering bug, invisible unless you're checking every number. The fix was small and precise. Tell the scheduler that those spill loads are a barrier it is not allowed to reorder across. A few lines in exactly the right place. And the payoff was large. The corruption vanished. Correctness jumped to 904 out of 947, with 0 regressions. And a whole optimization pass that had been forbidden became usable again. This is the kind of fix worth contributing back upstream. It helps everyone who uses this driver, not just us. Now we come to my favorite part of the whole project, the decisive experiment, the transplant. For the entire talk, we've been reasoning that the speed gap must live in the compiler, because everything else is identical. But reasoning isn't proof. So we designed an experiment to settle it with a hard number. The logic is this. If the gap really is the compiler, then Apple's own compiled machine code, the exact bytes Apple's compiler produced, should run fast on our hardware, even when executed through our open driver. And if it doesn't run fast, then the gap is something else. A hardware path difference, a driver difference, and we'd need to rethink. So here's the move. We capture Apple's compiled matrix kernel on macOS, the actual machine code. Then we graft those exact bytes into our Vulkan shader, bypassing the Mesa compiler entirely for that one kernel. Same silicon, the same instructions Apple emitted, but reached through the open Linux driver. It's a clean, direct test of the central hypothesis of the project. But there's a catch, and it's a brutal one. Running Apple's instructions is the easy part. Feeding them is the hard part. Apple's kernel expects all its inputs, the data pointers, the dimensions arranged in a very specific, completely undocumented way. And if you get that arrangement even slightly wrong, the GPU wedges and the machine reboots. Reverse engineering that arrangement was the real work. To feed Apple's kernel, we had to reverse engineer the handoff, the invisible contract Apple's compiler assumes between the setup code and the kernel body. None of it is documented. We recovered it by statically analyzing Apple's disassembled code, and by careful, dangerous probing on the hardware. 3 findings mattered. First, where the inputs go. Apple's kernel reads its buffer addresses and matrix dimensions from specific numbered slots in the shared uniform storage. We had to map each slot precisely. This slot holds the output pointer, these 3 hold the dimensions, and so on, and discover that the slot numbering is measured in 16-bit units, which had quietly corrupted our earlier attempts. Second, preloaded registers. The kernel expects certain per-thread pointers to be already computed and sitting in specific registers before it even begins. Normally Apple's own runtime computes and places those. We don't have Apple's runtime, so we had to compute them ourselves and inject them. And third, the subtle one that cost weeks. When the kernel writes a value into that shared uniform storage, that write is invisible to the kernel itself, because the uniform values are snapshotted once at launch before the kernel runs. So we couldn't seed the inputs from inside the kernel. They had to be seeded earlier, back in the setup preamble, which is exactly why I told you to remember the preamble. Together, those 3 findings turned a kernel that stubbornly output nothing but zeros into one that produced bit-for-bit correct results. I want to dwell for a moment on how you even debug something like this, because the transplant was reverse engineering on a machine that punishes mistakes brutally. The stakes are these. If you seed even one pointer wrong, the kernel starts reading random memory. The GPU wedges instantly, and the whole laptop reboots. There's no gentle error message. You just lose the machine for a couple of minutes. We lost it to this over and over during the transplant work. So the debugging tools had to be designed to survive that environment. The first technique is fill and check. Before running, we prefill the entire output buffer with a known junk pattern. Then we run the kernel and look at which cells changed. The cells that are still junk are places the kernel never wrote. And that pattern of what got written and what didn't tells us an enormous amount about whether the kernel is even executing the way we think. The second is bracketing the failure. We inject a little marker store, write a known value here, at successive points inside Apple's code. Then the last marker that actually survives tells us precisely where execution died. It's like binary searching for the crash, one careful probe at a time. And the third, which saved the hardware repeatedly, simulate first. Because the community reverse engineered the instruction set, we have a software model of it. So we can run Apple's tricky control flow logic on an ordinary laptop processor, in simulation, and confirm it behaves before we ever risk the real GPU. Test in the safe place, then commit to the dangerous one. That's what made a project this fragile actually tractable. Here's the actual machinery that made the transplant work. It comes down to two small hooks we added to the open driver, plus a hand-built adapter. The first hook seeds the setup. We splice a small blob of our own code into the preamble, the setup phase that runs before the kernel. That blob loads the real buffer addresses and writes them into exactly the slots Apple's kernel expects to read from. Because it runs in the preamble, its writes are visible to the kernel, solving that invisibility problem we just discussed. The second hook grafts the body. It replaces the normally compiled kernel body with Apple's exact captured bytes, and prepends a tiny prologue that computes those preloaded per-thread registers the kernel assumes are ready. And the result was the payoff of the entire project. The output matched Apple's reference to the very last bit, completely, bit for bit correct. And it ran at about 1530 gigaflops in the test harness. Apple's own kernel, executing through the Open Linux driver on the same chip, producing the same answer. That's the hypothesis confirmed. The hardware in the driver path are not the bottleneck. The gap really is in the compiler's code generation. There's one postscript worth mentioning. The hook that made this work had never been saved into the driver's version history. It survived only as a live, uncommitted edit on the machine. Rescuing that and committing it safely was, in fact, part of today's work before this presentation. It's worth stepping back and asking, how fast could this possibly go? Because knowing the ceiling tells you whether the remaining fight is even worth having. 3 numbers bound the problem. The first is the hardware's raw limit. In a tight, focused micro-benchmark that does almost nothing but feed the matrix engine, this chip reaches about 2050 gigaflops. That's roughly 89% of its theoretical maximum. So the silicon genuinely has the horsepower. There's no hidden hardware wall far below where we're operating. The second number is what Apple actually extracts on the real, messy workload, with all the dequantization and addressing and memory traffic that real inference involves. Apple's kernel runs at about 1730 gigaflops, so Apple gives up some of that peak to the messiness of the real problem as anyone would, but keeps most of it. And the third is our transplant test. Apple's exact bytes running on our open stack at about 1530 gigaflops. That we land close to Apple here, running the same instructions, is the confirmation that our hardware path is sound. Put together, these 3 numbers tell a hopeful story. The chip has the raw power. Apple extracts most of it, and we are within striking distance. The gap between our production kernel and Apple's is not a hardware ceiling we've hit, it's code generation we haven't finished. That's a very different, and much more motivating, situation than being blocked by physics. It's important to be clear that this is not a solo effort in a vacuum. It sits inside a larger, public, collaborative push to make open-source graphics genuinely competitive on Apple Silicon. And that context matters both for credibility and for where it goes next. The wider effort is coordinated in the open, in a long-running public discussion thread involving the Asahi graphics developers and a handful of other contributors, all comparing notes on exactly this problem. Why is the open matrix path slower than the vendors, and what closes the gap? Working in public means results get checked and built upon rather than lost. There's also encouraging evidence that the approach scales. On a larger Apple GPU, one with many more cores than our little 7-core part, a contributor reported the open matrix path already reaching over 1,000 tokens per second. That tells us the fundamentals are sound. The technique isn't hitting a wall, it just has less headroom to hide latency on the small chip we're using, which is exactly what the occupancy story predicts. And the collaboration flows both ways. A scheduler improvement that originated with another contributor was ported onto our 7-core chip. And in return, findings from our work, like the schedule ordering bug we fixed, feed back upstream. That last point is really the whole philosophy. A fix like that belongs not just to us, but to everyone who uses this driver. Contributing it back is the entire reason to do this work in the open, rather than in private. So where does it all stand, honestly? The trajectory is clear. An early scalar approach ran at 91 tokens per second. The open stack today runs at 210, and 220 with the scales optimization. Apple's reference sits at 272. We're at roughly 80% up from a third, on the same hardware with an open driver. And crucially, we now understand the remaining gap. The Transplant proved it. When Apple's exact compiled bytes run on our stack, they run fine. So the missing 20% is not the hardware and not the driver path, it's the compiler's code generation. Our compiler emits nearly 5 times the instructions and uses far more registers for the same math. The open lead is concrete and measured, not a mystery. About 100 of our 159 registers are addressing and dequantization overhead. Cut into that, cross one of the occupancy steps on that staircase, and more threads come online. That's the next real gain, and it's pointed at a specific number. And I want to end this part on the right note. Nothing here is closed. Every result in this talk is reproducible from a written recipe. Every dead end we hit is a mapped path, not a wall fully open to revisiting with a fresh idea. This is a project in motion, not a finished report. Before the closing thoughts, one slide on something that's easy to undervalue but absolutely central: durability. A performance project is only worth as much as it is reproducible. A pile of clever results that live in one person's head, or on one laptop that might get wiped, is worth almost nothing to the next person. So the final step of this work was making sure none of it can be lost. The Transplant is the clearest example. The captured Apple kernel, the reverse-engineered interface, and the driver hooks that make it run. All of it is now captured, documented, and committed to version control. And remember that one crucial hook that existed only as a live, unsaved edit on the machine. That was rescued and preserved in several independent places, so a rebuild or a reflash can never erase it again. The shipped optimizations live in the open histories of the llama.cpp project and the Mesa driver. The reverse engineering notes, the disassemblies, and the reproduction recipes live in the lab repository. And that's mirrored to more than one host, so no single failure loses it. Crucially, every result is reproducible from a written recipe. The exact commands to rebuild the driver, rerun the benchmark, and re-verify correctness. A fresh person can confirm any number in this talk for themselves, from scratch. And maybe the most valuable thing preserved isn't code at all, it's the reasoning. Why each dead end was a dead end. That's what stops the next person from blindly rewalking a path we already know leads nowhere, and lets them start from the real frontier. Let me close by pulling back from the one benchmark to what this project really shows. First, open beats closed when it's given a foothold. A community-built, reverse-engineered driver got within 20% of Apple's own tuned stack, on completely undocumented silicon. And we don't just have a number, we know exactly what closes the rest of the gap. That's a remarkable place for an open ecosystem to be. Second, measurement is the moat. This whole field is full of tempting results that are fast because they're wrong. The correctness oracle and the perplexity gate are what let us walk through that minefield and keep only the true wins. The discipline wasn't bureaucracy, it was the thing that made the numbers mean something. Third, reverse engineering pays off enormously. Being able to actually read the hardware to disassemble it, diff our code against Apple's, and ultimately transplant Apple's kernel wholesale, is what turned a vague, it's slower into a precise. It's these 103 registers of overhead. You can't optimize what you can't see. And finally, everything here is preserved. The captured kernel, the reverse-engineered interface, the driver hooks, the reproduction recipes, all committed to version control in multiple places and fully reproducible. So whoever picks this up next doesn't start from zero. They start exactly where we stopped. Thank you for watching.